In this lecture, we study countability. So, goal of this lecture is following: generating more examples of countable sets. Okay, so goal. Goal of this lecture is following: generating more examples of countable sets. More examples of countable sets. So far we have studied the following things. So last time, so we have defined countable sets. So first we have defined the following. Consider a map or function from x to y bijective function. So x and y, these are two non-empty sets. So if there exists a bijective function f from x to y, then we say that x and y are equivalent. X is equivalent to y, and this this is a so this is an equivalence relation. Basically, this is reflexive, symmetric, and transitive. This is an equivalence relation. Then we have defined x, a set x is countable if x is related to n. Okay, that is if there exists a bijective function from x to n or from n to x. Okay, then we have given an example explicitly. We have shown that the set of all integers, this is countable, that is set of all integers z, this is equivalent to n, that is z is countable. Then we have generated more examples of countable sets, namely we have proved two theorems. First one, every infinite subset, of a countable set is countable. Of a countable set is countable. Next, we have proved. Next, we have proved countable union of countable sets is countable. Countable union of countable sets is countable. So this time, the next page. This time we define at most countable sets. Define at most. This time we will define at most countable sets. Next, we generate more examples. We prove that Cartesian product of countable sets is again countable. So if x equal to x1 Cartesian product with x2 and so on Cartesian product with xn. So finite Cartesian product of x1, x2 and xn, this is countable if xi's are countable for I equal to 1 and so on. And also we show that the set of all rational numbers, this is countable, and as a corollary of 2 also we show that and Qn, so Cartesian product of n copies of rational set of rationals Q cross and so on cross Q, this is n-fold Cartesian product, this is countable. And also n cross n, where n is set of all integers, this is also countable. Next, we study uncountable sets, namely we prove that uncountable. The set of all sequences in 0 and 1, sequences in 0 and 1, that is binary sequences, set of all binary sequences is uncountable, sorry, this is uncountable. And as a corollary, we will show that open interval 0, 1 is uncountable, and hence set of all reals R is uncountable. Okay, so let us start with the definition of at most countable sets. Definition. Most countable sets. So sets we can divide into two categories. This is finite and infinite. And here we have countable and uncountable. So this type of sets, finite and countable sets, these are called at most countable. Okay, so we define following: a set X is called at most countable if it is means if X is either finite or countable. That is X is related to n sub n, or X is related to set of all naturals, and this is equal to set of all natural numbers 1, 2 and up to n. Okay. Well, recall that last time we have proved the following theorem. If n belongs to set of all naturals, this is a collection of countable sets, collection of countable sets, then the union of these countable sets in belongs to set of all naturals n. So this is basically countable union of countable sets. Then S is also countable. And as a corollary of this theory, we state that corollary, suppose lambda subset of set of all naturals, suppose lambda is at most countable, at most countable, and this is n belongs to lambda is a collection of at most countable sets, at most countable sets, then the union is equal to union en over n belongs to lambda is also at most countable. Okay, so basically, if you replace countable by at most countable in this theorem, so that's statement is also holds true, and we give the proof of this corollary as an exercise. The exercise prove the corollary. Okay, so now we move to the next item. Basically, we prove that Cartesian product of finite Cartesian product of countable sets is again countable. So Cartesian product and countability. Cartesian product and countability. So let us state the theorem. So here is the main theorem is following theorem. Okay, so let me label this is theorem 1, corollary 2, and this is theorem 3. Okay, so here is the statement. Let x1, comma, and so on, xn be countable sets. Countable sets. Then x equal to the Cartesian product of x1 and so on, xn is also countable. Okay, so first before going into the proof of theorem 3, we consider some particular cases. So in the following lemma in the following lemma, we prove that if x and if so in the following lemma we prove that if x is countable, then x plus x is also countable. And in particular, n cross n is countable. So in particular, when x equal to set of naturals, then this statement in particular n cross n, this is also countable. So now we prove lemma 4. So by hypothesis, what is our hypothesis? Hypothesis is x is countable. So there exists x is countable implies there exists bijective function let's say f from x to the set of all naturals. So there exists a bijective function f from x to the set of all natural numbers. Now we define capital F from x cross x to the set of all naturals by f of x comma y. This is equal to 2 power f of x times 3 power f of y for all x comma y in x cross x. Okay. Then f is injective, then it is straightforward to see that f is injective and this is infinite set, therefore this is countable, and therefore it follows that x cross x is countable. Okay, now in the following lemma, now we prove our second lemma. This is okay, so lemma 5. If x and y are countable, then the Cartesian product x cross y is also countable. So proof, we have a similar proof here. So x and y countable implies x and y countable implies there exist bijective functions f1 from x to the set of all natural numbers and f2 from y to the set of all natural numbers. Now we define let's say h from x plus y to the set of all naturals, okay, by h of x comma y, this is equal to 2 power f1 of x times 3 power f2 of x. And then this function is, again, it is straightforward to see that h is injective. and it follows that x cross y is countable, because x cross y, this is infinite set. Okay, so this is, and we have injective function h from x plus y to set of all naturals. So therefore x cross y is countable. Okay, so now we are ready to prove that. Uh, so basically now we are ready to prove the theorem 3. Proof of theorem 3. Proof of theorem 3. So now x1 and x2 countable implies x1 cross x2 is also countable. This is by lemma 5. Now this is step 1, and in step 2 x1 cross x2, and so from step 1 what we have, this is countable. Now this is countable, and given that x3 is countable, implies x1 cross x2 then cross x3 is countable. Okay, and this is, and x1 cross x2 cross x3, this is equivalent to x3, this is equivalent to the Cartesian product x1 cross x2 cross x3, and this implies x1 cross x2 cross x3 is also countable. So by induction, we conclude that x1 cross and so on cross xn, this is countable for any natural number little n. Okay, so next corollary. So first we prove the following lemma, then state lemma. Q, the set of all rational numbers, this is countable. So we have injective. So first of all, Q is infinite set, and we have from Q to set of all naturals, injective function defined by f of p over q. This is equal to 2 power p times 3 power q. So this is injective function, implies q is countable. And as a corollary, so this is lemma number 6. And as a corollary, we level by 7. As a corollary, we say that q cross and so on cross q. This is, let's say, n-fold Cartesian product of set of rationals. This is equal to q power n. This is subset of Rn. Okay, so Qn, this is countable subset of Rn. Okay, so now we study an uncountable set. And so namely we prove that the set of all sequences in 0 and 1, that is uncountable. Let us go to the content. So we have defined at most countable sets, and also we have proved that um, uh, n-fold for any n natural number, n-fold Cartesian product of countable sets is countable, and also we have proved that q is countable, and hence q power n is an n-fold Cartesian product of set of rationals. This is also countable, and also we have shown that n cross n is also countable. Now we prove this uh, result. The sequence in the set of all sequences in 0 and 1 is uncountable set. Okay, so state as a theorem, so level by 8, theorem 8. Let X be the set of all sequences, be the set of all sequences whose terms are the digits 0 and 1, whose terms are the digits 0 and 1. X is the set of all sequences uh, with terms 0 and 1. Then X is uncountable. X is uncountable. The proof is very simple. The proof is by contradiction. The proof of the theorem is by contradiction. So we assume that X is countable. Assume that X is countable, and finally we uh, we reach to some contradiction and conclude that X is uncountable. So I assume that X is a countable set. So if X is countable set, so then it admits an arrangement in a sequence as a sequence of distinct terms. So consider an arrangement of the elements in X, of the elements in X in a sequence of distinct terms. Sequence of distinct terms like f1, f2, f3. So X equal to f1, f2, f3, and so on. So let us write f1. This is equal to, this is sequence in 0 and 1. So let's say x11, x12, x13. So this is f1 is a sequence, x14, and so on. So where x x1 n belongs to the set 0 1 for every n belongs to set of all naturals, and f2 this is equal to x21 x2 comma 2 x23 x24 and so on, and similarly f3 f4 and so on. So let me write f3 this is equal to x31 x32 x33 x34 and so on. This is equal to x41 x42 x43 x44 and so on, where xij or let me write xmn belongs to 0 1 for all n belongs to set of all naturals. Okay, now we define. So basically if you take, if f belongs to x, then there exists some n in the set of all naturals. This means that if f belongs to x, then there exists some n in the set of all naturals such that f equal to fn. Okay, so now we construct a sequence capital F. This is equal to, we arrange in an array x1 x2 x3 and so on, where xn belongs to 0 1 minus xnn. Okay, then now in this set two sequences are equal if they are component wise equal. Okay, so now see that this sequence f is not equal to so first of all this sequence belongs to, by construction f belongs to capital X, because f is a sequence in 0 and 1. Okay, now note that f is not equal to a small f n, because the nth component of, or nth term of the sequence capital F, because that is xn is not equal to xnn. Okay, so this is nth term of small fn, and xn is nth term of capital F, and they are not equal as xn. By construction xn belongs to 0 1 minus xnn. So xn cannot be equal to small xnn. So this is a contradiction. So as you know that if f belongs to capital X, then there should exist some little n natural number such that f equal to fn. But here we don't have natural number small n such that f equal to f small n. Okay, so this is a contradiction. Thus we conclude the proof. And here we have an exercise. If x is equivalent to y and one of them, let's say x is uncountable, then y is also uncountable. And now as a corollary of theorem 8, we prove that the corollary we prove that the open interval 0 1, this is uncountable, and by this exercise, and hence the set of all reals R is uncountable, because R is equivalent to the open interval 0 1. So before we stop, we prove that this is uncountable. So if x belongs to open interval 0 1, then x can be written as 0.x1, x2, x3, and so on. Okay, where xi belongs to, this is xi belongs to 0, 1, 1, one of the decimal digit. Okay, up to 9. So here the proof is, proof. Proof of corollary. Corollary, we may label it by 9. Proof of corollary 9. So again, the proof is by contradiction. The proof is by contradiction. Assume 0 1, this is countable. Then we have a sequence f1, f2, f3, and so on, which is equal to open interval 0 1, and this is equal to f1 belongs to open interval 0 1, so we can write f1 as 0.x11, x12, x13, and so on. This is equal to 0. X21, X22, X23, and so on. This is equal to 0.x31, x33, this is x32, and this is x33, and so on. Okay, where xij belongs to the set of all decimal digits 0, 1, and so on up to 9. Now we define if this is equal to 0.x1, x2, and so on. Okay, where xi belongs to 0, 1, and so on, 9, minus x in n, or xi belongs to, so xi, and we choose this xi such that not all xi is equal to 0, so that not all xi is equal to 0 and 9. Then f belongs to 0, 1, and f is not equal to fn for all n belongs to set of all naturals, as x n not equal to x n n. Okay, therefore f is a member in the open interval 0, 1, but f is not equal to fn for every n belongs to set of all naturals. Therefore this implies x equal to 0, 1 is not countable. So this is a contradiction, and we conclude that. Right. So this is contradiction, and we conclude that 0, 1 is uncountable. This is uncountable. Okay. So we stop this lecture here.